Explosives play a very crucial and enabling role in today's industrialized society. But because of its power and destructive capabilities, they have been used to threaten or harm society as well. ALERT's research in detecting and characterizing explosives is helping first responders and security understand and locate explosive materials before they can be used for malicious reasons.
All right, if someone is carrying a threat or is bringing a threat into an airport or an environment where people are gathering, we want to be able to detect that threat as quickly as possible so that we can intervene and remove that threat from where people are assembled before the threat gets anywhere near a potential target. And the effectiveness is important because we want to make sure that we're only taking action when it's appropriate. We're not disrupting people's everyday lives unnecessarily.
In order to find the threat of explosives and notify people, ALERT has to be able to classify what materials are explosive and what aren't. This rigorous and detailed analysis is key to understanding what exactly an explosive is.
So I have described explosives as chemicals. What makes them special chemicals? That's rather a hard question to answer, and it's something we look into. But we define an explosive as something that can detonate. A detonation is a shock wave that moves faster than the speed of sound in the material. So the demo I usually do is I hit a table and show a pencil vibrating and rolling off the table. The reason the pencil vibrated and moved was because the shock wave was going through the table. That was traveling at the speed of sound in the table. An explosive, when it detonates, moves faster than the speed of sound, so it can't be quenched. This makes it a special chemical. Its requirements, generally, it has to release heat when it decomposes, and lots of things do. Wood releases heat when you oxidize it. It has to give off gas. Again, a fire example works for giving off gas. And then the very special requirement is it does it very fast. It does it fast enough that the energy release supports that very special shock wave, that detonation wave. In our laboratory at University of Rhode Island, we've been doing explosive research for many years. As members of ALERT, we're very much focused on explosive detection, which means we go back and look at those explosive properties, characterize them, provide them, but also look at what properties might be amenable to a different detection technique.
As the University of Rhode Island records the results from the various tests, they populate a very unique and helpful database.
A number of years ago, I realized that forensic labs don't necessarily have all the different kinds of explosives that they might run into. Specifically, nowadays we see something called homemade explosive, which may or may not be made in a home, that they might not have as an exemplar. So therefore we decided to make a database of certain explosive properties. Now explosives, in their basics, are chemicals, and all chemicals have certain properties. Their interaction with certain kinds of stimuli. The most common one is you recognize an object because you know what it looks like. You're reacting to a visual stimuli. You're reacting to the color of light that's coming into your eye and the shape. That's not particularly helpful with recognizing a chemical, but there's other kinds of stimuli that are very characteristic of a particular chemical. Now I'm referring to the explosives as chemicals because indeed they are chemicals. They're just very special chemicals. So we record the same kinds of properties that are recorded with all chemicals. It's just unusual to have a database of explosive properties. And what we look at is infrared, Raman, nuclear magnetic resonance, both pulsing for carbon and for hydrogen, mass spectroscopy, and differential scanning calorimetry, how they react to heat.
Empowered by the data in the explosives database, researchers within ALERT can develop sensors that can react when the presence of these explosive chemicals are sensed in the environment.
If somebody makes a bomb, some sort of explosive, they're likely to leave a fingerprint that has some of that explosive residue on it. They might leave that on the box that they were handling. They might leave it on their coat. They might brush their hand across their sleeve. Trace sampling is finding those tiny residues, those minute residues, those traces on the surfaces that were touched, or perhaps sniffing the air around those regions and finding any that might have gone from the solid phase to the vapor phase.
Finding such small amounts of anything is one of the main obstacles in detecting explosives.
Well, by their nature, trace explosives detection is a difficult challenge. We're looking for very small quantities of material on surfaces or in the gas phase. And one of the interesting technologies we're working on right now involves a chaotic cavity. It's about the size of a baseball. And you can imagine if a molecule goes into the vapor phase and very, very few molecules are in the vapor phase, which happens with explosives, you're not necessarily going to have an easy time sniffing them. So what this technology does is the size of a baseball, and we shine light into that cavity inside that baseball. But it bounces around in such a way that effectively the light travels the same distance as the pitcher's mound to home plate on a baseball field. So we have many, many, many more opportunities to sense those very few explosives molecules in the vapor phase in this chaotic cavity than we would ever have in such a small space. And right now we're working on that in the laboratory and hopefully getting ready to deploy that in airports or other locations.
The technique utilizing the chaotic cavity seems to have great potential in detecting explosives out in the field when they are in the vapor phase. But detecting explosives still in the solid phase is another challenge being met by alert researchers.
So if we're trying to find an explosive residue that's on a surface, then that surface is going to be rough, and there's maybe a thumbprint of residue on the surface. That residue will be pressed down into the rough regions on the surface we care about. So my swab you should think about as a nano-engineered toothbrush or maybe a sea anemone. It has individual fingers that can move independently, but the ends of the polymers have special chemical head groups attached. And those chemical groups we put on the ends of the polymer fingers in our swabs have very strong chemical interactions with the residues, and they're very specific for the chemistry of the residue. So when they get close together, they attract and hold the residue very closely.
Clearly, stopping people from using explosives in a dangerous or harmful way is a desired outcome of alerts research. But accidental detonation of explosives is also an event that alerts researchers would like to see less of. By educating people about the dangers and necessary safety precautions needed to safely handle these volatile substances.
In our laboratory, when we make explosives, whether we're doing chemistry or whether we're doing mixing, we have safety protocols that we follow. You might say the golden rule is think about what you're doing, do it again, think about it again, and then ask somebody else if that makes sense. All right, so you think about it to the point that you write it down and have somebody else take a look at what you're doing. And the other principle is minimize. When we're doing research on explosives, we always work with the minimum amount we can. We expose the minimum number of people to the danger, and we do it for the minimum amount of time. This is not a spectator sport. This is very serious business, and you can get seriously hurt. So I leave you with that warning. Thank you.
ALERT still has many goals to achieve and many challenges to meet on its way to providing the understanding and technology needed to stop the harmful use of explosives. Sampling remains one of the most difficult problems to get around in this research area. ALERT is pursuing other methods that may allow for standoff detection methods in order to alleviate this problem. In the years to come, ALERT will continue to extend the state-of-the-art while exploring solutions for the challenges of the future.